Hey guys, what's going on? So today we're going to be talking about interaction theory. Before we get into this, just want to reiterate, we went over talking about the proto-Lagrangian, we went over talking about the Dirac-Lagrangian, building those Lagrangians from group theory. Now what we want to do is we want to take those ideas and we now want to talk about how these interactions, or these fields, will interact with each other to generate what we're going to call interaction theory, okay? This is very important for what's to come, and it's going to lead to very important notions later on also to help us understand quarks, leptons, and all those kind of stuff, all those kinds of particles. Also, if you are interested in this kind of content, you can make sure also to hit up my Patreon page, where instead of early content now, I'm sort of moving into the direction of putting exclusive content, because again, these videos they take somewhat of a good amount of time to make and to prepare, and so I'm moving on into the realm of making exclusive content for those of you who want to know more about advanced physics, modern physics, and different areas of science. With that being said, part of this is going to be in that video, okay? I'm going to be talking about broader implications of interaction theory, which is going to make this video a little bit longer on my Patreon page, but you get more information there as opposed to what I teach here. Anyways, let's get into the content right now. Make sure to hit that like and subscribe button. Now let's get into it. So we are talking about interaction theory. Interaction theory is going to be very, very important for what we're going to be talking about later. So what we first want to talk about is the concept of global and local transformations. So what is a global transformation? A global transformation essentially is one that looks like this. We have a field configuration, and that evolves into a new field configuration. And that new field configuration is a function of our previous or the old configuration. And this is what it means for it to be a global transformation, right? So e to the IA, where a is a constant. It doesn't depend on anything. So this essentially means you're shifting the field configuration by some constant. Everywhere, it doesn't matter where you are in the field, everything gets shifted by a constant. And we can do the same thing for a conjugate field. We just have to complex conjugate that U1 transformation, okay? And so these two guys define what are global transformations, which is what we're going to use to define global invariance later in a few minutes here. A local transformation looks like this, right? So that a factor in the exponential actually depends on space-time here. So this means depending on where you are in space-time, each location within that field gets shifted a certain amount, and it actually depends on where and when the spatial and temporal components of that field, that each and every point in that field is shifted a different way. Okay, that's what it means for there to be a local transformation. Okay, so global transformation, everything's shifted in the same way, or everything's transformed in the same way. Local transformation means everything is not shifted in the same way. It depends on where you are in that field. So essentially, a global and local transformation means that we're going from e to the IA to e to the IA as a function of spacetime. Okay, spacetime. So let's get into now a global transformation of the Dirac-Lagrangian. So this is our Dirac-Lagrangian, right? So here I've labeled it as 1/2 0, the 0 1/2. This just explicitly tells us that this came from group theory. And what we want to do is we want to say, okay, our primes, right? Those are these guys right here, or more specifically, these guys right here. This is what they look like. So we'll just plug them in right here. And since this derivative here is a derivative the derivative with respect to spacetime coordinates, since there's no spacetime coordinates in this, we can just bring it on the side of the derivative and we can cancel them out. Same thing here. We can cancel these exponentials out as well because of that complex conjugation. And what we get is something that looks like this, which looks like this, right? The same structure here between the shifted and the original Dirac Lagrangian. So that means that there's symmetry involved. And so under a global transformation, the Dirac Lagrangian is invariant. And again, we think about this. Think about a field and shifting everything. Okay? If you shift everything in the same way, then there's going to be global invariance. Nothing really is going to change about that field. However, when we do a local transformation, things might be a little bit more hazy. And the reason for that is precisely mathematically, the reason for that is because of this derivative. When we make this as a function of space-time, we all of a sudden can't just move it over here and cancel things out. What we have to do is perform the product rule, right? So when we perform the product rule, we get something that looks like this, right? So the derivative of this here, right, so I've just written it right here, is going to be this, okay? And I don't have this here because I've already sort of pre-canceled that out with this right here. So these two guys, here, I'll actually write this out a little bit more explicitly. Let's see, I'll expand things out. So I'll just take these guys and move them out a little bit. And I need to put my E to the IAX. And then what's going to happen is that these two guys will cancel. But anyways, that's what we're doing right here. We're doing the product rule because of this derivative. So because of the derivative in the Dirac Lagrangian, local transformations are actually, what they actually end up doing is making things not locally invariant, right? Because now so we have this term, which was this right here, and then we have this term here, right? So this term right here is right here. These two guys are going to cancel, giving us this, okay? And then we have, I need to move things around again because we need our other field value, or our other field, right? Because we have this right here, which is right here, and then these guys right here. And what ends up happening is we have a term that looks like this. Okay, so let's keep this in mind, right? This here is our Dirac, looks like our Dirac Lagrangian, but then we have this term here. I'll underline that in a different color. We have this term here, which is this is not something that was originally in our Dirac Lagrangian. So what does that mean? That means that our Dirac Lagrangian is actually not symmetric. So under local transformations. So when you move everything around locally, or when things on that field move not constant with respect to everything else in that field, then things actually get messed up on that field, and it's not locally invariant. It looks different under transformations where everything sort of changes as a function of where they are in space-time. So we're going to have to remedy this somehow. And in order to do that, we need to think of the Proca-Lagrangian first. So to do this, let's consider first a global transformation for our Proca-Lagrangian. Now, keeping in mind that the Proca-Lagrangian describes vectors, right? So this is the global transformation for a vector field. Okay, for our Dirac Lagrangian, we needed that exponential, that e to the I, because the Dirac Lagrangian fundamentally it's a complex field. However, for our Proca-Lagrangian, these are normal 4 vectors, right? So this is what our global transformation looks like. However, this is what our local transformation is going to look like, and we'll come to that in a few seconds here. However, let's take a look at what this global transformation looks like for the Proca-Lagrangian. So this is what the Proca-Lagrangian looks like. Okay, and we expand everything out, and because A is a constant, then that means that we get these two guys back, but then we get this guy. Now we can essentially ignore this if we say m is equal to 0, right? M, as you've maybe recalled if you watched my quantum field theory playlist, m is a constant that tells you the degree to which the field is interacting with itself, which is it's a self-interaction term. However, if we say that m is 0, then we can actually say that this is invariant under global transformations, right? So the Procol-Lagrangian is invariant under global transformations, as we can see right here, if m, or if the mass associated with that field is 0. So for a particle with no mass, then the Procol-Lagrangian is symmetric under global transformation. Now let's take a look at local transformations. We're going to call this the Maxwell-Lagrangian now. The Maxwell-Lagrangian describes photons. Photons have no mass, so we're going to ignore that mass term. Okay. So so we put everything in, right? So this is what A prime, these are what our A primes look like. And we get, when we FOIL everything out, as this big, long, ugly thing, right? So things are going to get ugly before they get pretty. That often happens in physics. Anyways, because everything on the side of the equation has basically dummy variables in it, we can swap dummy variables around. And that's because nothing's constraining them on the side of the equation. We don't have any mu's or nu's here. So we can swap here, and we're going to swap here. And when we do these swappings, we can find that this term is the same as this term. This term is the same as this term. The only difference is their signage. So we can cancel those guys out. And these guys also end up canceling out when we do this in swapping of the dummy variables. Now, and again, if I'm going too fast, you can always pause the video, but now we have this term right here, and this term right here is the exact same thing as we have up here with the exception of the primes, right? This is invariant. It's the exact same, so it's invariant. So that means the Procol-Lagrangian, or the Maxwell-Lagrangian, is actually invariant under local transformations. So this Maxwell-Lagrangian is globally and locally invariant. Whereas the Dirac-Lagrangian is only globally U1 invariant. And these were those global transformations. Those transformations, the global and the local. And then for the Dirac equation, we had our global was psi going to psi prime, which equaled psi e to the I a, and then our local transformation was psi going to psi prime, which equaled psi bar e to the minus I a x. Our global also for our complex, you kind of see how this goes, right? This is just how I'm just reminding ourselves of what these transformations look like. But you can also have, again, the global transformation for the complex case, and you can have the local transformation, or not the complex case, for the conjugate, and then you can have local transformation for global, or not, local transformation for this would be for the conjugate, and this one would be not, this one right here would not be for the conjugate. But then you sort of get the point here, right? So we need U1 invariance for the Dirac equation, right? Because the Dirac equation fundamentally came from, fundamentally is a complex Lagrangian. Anyways. Okay, so we're putting pieces together here. So what we want to do is we want to find a Lagrangian that's globally and locally invariant. However, the Dirac-Lagrangian, we want to find a Dirac equation, or Dirac-Lagrangian, that's globally and locally invariant. Because then in that way, we can get, That's where the interesting physics comes from. Because again, we were looking at invariant quantities when we were building these Lagrangians. So now we want to consider this term right here. We're going to add this term to our Lagrangian. But before we do that, let's just take a look. If we locally transform this interaction Lagrangian, excuse me, if we locally transform this, what we get is something that looks like this, okay? And we could see automatically, locally transforming these guys, well, those guys are just going to cancel, right? Because there's no derivative term in here. There's no derivative term. So I can put those in here right now. It's just going to be a little bit longer of a calculation, not that much longer though, right? They're just going to cancel. There's no derivative in this term, so why bother? Anyways, we can FOIL things out and we get this, and if we notice, we have this term right here, which is also right here, right? Derivative of that, these two guys, and this is just -1, and we have a +1. So this is interesting, right? Because if we add this term, then that would seem to suggest that this term would seem to suggest that if we added it to our Dirac Lagrangian, then we can get rid of this term. Okay. So let's do that. So we start, here's our Dirac Lagrangian. We're going to add this interaction term. And we're going to add this G right here also. This is going to be the degree of interaction between our spinors and our vectors. And we'll talk about that later. Okay. So here I have so this here is our transformed Lagrangian. Okay, this is what we had right here. Okay. Here's that I squared, here's that term, and then here's these two terms. This was our transformed Dirac Lagrangian. This is still that term right here. All right. So now so now we have all this here. Okay, and we have this here now. So if we transform the A, okay, so transforming the A into this, right? So we're doing a local transformation of this guy, which is right here. We split, that's what this is right here. So this guy splits up into these two guys. And then we have all of this, right? Things get ugly before they look nice, but we're getting there. All right, so this becomes -1. We keep these guys, nothing changes yet. But now, here's what's interesting. If we take these two guys are the same, right? So we factor this guy out, and we have is a G and a -1. So G -1 plus this term right here. So now we have this. And if we say that G equaled 1, then this whole thing is going to go to 0. So if G equals 1, we get this. There you go. We have we've regained the structure of the Lagrangian. Right. So by merely adding this term, we now have achieved local invariance. This was our locally transformed Dirac Lagrangian, and by adding this term here, we've now achieved local invariance. So there's a very interesting link between interactions with a vector field in this case, and this is going to be very important to note, because the theme going forward is going to be an interaction with some vector field is going to fix our local invariance problem. Okay, and this is a theme I really, really want to hit home here, because interactions are going to be the answer to local invariance. Okay, if we want to retain local invariance, we need interactions with with these vector fields, essentially. Okay. So what I want to do here is stop, okay, because the rest of the video is going to be on Patreon. Okay. This part of the following part, we're going to see that link between what exactly the meaning of this G is. Where's that G that I have? This G right here. And we're going to sort of talk about it and its relationship to the mass of the fields, how exactly the mass of the fields change. We also want to take a look at how we can tidy things up here and make our Lagrangian look really beautiful, look really nice under these types of invariances, and that or under these types of global and local transformations. And we're going to talk more broadly about what's to come later. So again, if you like this kind of content, make sure to hit that like and subscribe button. If you want to get exclusive content, you can go on to you can go onto my Patreon page now and view the rest of this video with your contributions. Make sure to hit that like and subscribe button. Hope you guys all have a great weekend, or not a weekend, right? So this is the start of the weekend. This is like a Wednesday. So, anyways, I will see you guys in the next video.